Assalamu alaikum. My name is Abdullah Shahir, and I'm presenting a paper regarding recognition of handwritten Arabic shape letters. The title of my manuscript is Unsupervised Learning of Shape Segment Point Distribution Model with the EM algorithm. I'm associate professor at the Department of Computer Science and Information System at the Public Authority for Applied Education and Training. The abstract in this paper, we demonstrate how to classify and recognize handwritten Arabic shapes using 4 main models: segment point distribution models. We construct a unsupervised probabilistic framework to capture the modes of shape variation using segment point distribution models. In order to achieve that, we have used the EM algorithm, expectation maximization algorithm, which is an optimization algorithm that is a 2-step feed-forward iterative process, and then the classification using Bayesian factorization. The novelty of the work is the using point distribution models, but we use segment point distribution model, which means we use part of the shape. We use shape representation using unlabeled landmark without pre-processing steps. That means we do not use thinning algorithms to thin the shapes. We do not use shearing. We do not use hard rotations. We use very simple processing, pre-processing stage, such as translating and scale. That's it. We use a framework which is unsupervised. There exists in the literature 2 training algorithms: supervised learning and unsupervised learning. In supervised learning, the data inserted to the algorithms, it's labeled. Hence, the models are well known in advance. And unsupervised models, the data is unlabeled. Hence, the number of models are unknown until the end of the algorithms. The 4th novelty of the work is classification rates is reasonably high. But to give a understanding of the Arabic script, perhaps my colleagues here, they are from Saudi Arabia and understand this. This is better than any other non-Arabic speaker. The Arabic language is a native language for almost 700 million people, speakers. That's regarding the mother language is Arabic, but we have 1.6 billion people are also known Arabic because they are Muslims and they read Quran. So it's they know about the letters. Arabic writing is cursive, just like from right to left. Similar characters are Urdu, Persian, Sindhi, and Pashto, and all of them are different cultures from South Asia, Southeast Asia, Southwest Asia. Arabic script is written from right to left, such as Hebrew, Persian, Syriac, and Aramic languages. The Arab script is similar to English. Therefore, it consists of 28 letters, basic letters, while English is only 26 letters. The presence and absence of vowels diacritics can give different meaning. The Arabic letters also appears in 4 different shapes: beginning, middle, separated, and end of the word. To give more exact presentation about the diacritics, you see these are 4 different words, but they are assembled from similar letters. But with the adjectives, they give different meaning. So this is the importance of such characteristics to the language. So even though we share similar alphabets, cursive letters, it's different in meaning. You see, alam, flag, ilm, science, allama, taught, and ulm is noted. So it's different meaning, giving the location of characteristics either above or below the letter. The Arabic script is this. The Arabic script. This is just a sample of 28 letters. You see, this is the isolated part of the alphabet. This is the beginning. You see, the beginning. This is the median in the middle of the word, and this is to the end or the final of the word. So we have to train all of those to the alphabet. Okay, we have used two sets of training. We have used sets for training and sets for classification or recognition. So each pattern X, we donate that to XI, such a shape letter, is segmented into a series of non-overlapping segments. So the shape consists of non-overlapping segments, continuous non-overlapping segments, S sub I of 1, segment 1, segment 2, segment 3, until segments of K, where each segment consists of landmark representation. So we have set of landmarks for each segment. To elaborate more, this is a sample sets. This is scene. This is sample shape extracted from the sample set. This is the shape segment. And we have K shape segments. And this is the labeling of the segment for shape X sub I. So segment of training set 1, shape 1, segment 1, segment of training set 1, shape 1, segment 2, and therefore until the end of segments. This is the segmentation of the shape. The way to do that is because we have approached a different approach from dealing or processing the whole shape due to the complexity of the shape structure. Arabic shapes are, especially in writing, they are very different in writing from one writer to another writer. Therefore, to break the complexity, we segment the shape into a non-overlapping continuous segments. Why did we use the point distribution models? Because the point distribution models, they are generative models, and generative models where when they are trained, we can generate a similar shape, a shape that is similar to those in the training set. That's the powerful of the point distribution model. Hence, we use the mean shape of the segments. It's computed by S dash, and that's the sum of averaging all the segments through the training patterns. Of course, over T, the training samples, and from I1 to T, training samples, from K, the segments to N number of segments by the shape. We use the variance covariance. We construct the variance covariance matrix, which is the covariance matrix, the variance n-dimensional matrix, which is a point in the feature space. We construct that by giving the each training segment pattern minus the mean shape times its counterpart transpose. This is the mean shape and the covariance matrix. Having established the covariance matrix, constructed covariance, we use the eigenvectors and eigenvalues of the covariance matrix. The eigenvalues and the eigenvectors are a series of the direction and the variance of direction in a feature space. Hence, we solve the linear equation given the covariance matrix times the eigenvalues, because we extract the eigenvectors, and the eigenvectors are then ordered to the magnitude of the direction. The highest comes first, so it's descending. Okay. The aim, how to learn a mixture of point distribution models. The purpose of the study is to capture the variations of certain training set, in which the training set is about 2,000 shapes, and each shape is segmented into a non-overlapping segments. So the training set is massive, and that's only for training. For testing, we use different training set. We cannot use the same training set for testing and training. We use two different sets for training and testing. In order to do that, we construct a likelihood function. Likelihood function is concised by the probability density function, which allows all training sets for a sample sets, while T belongs to a model, the group of model or the sets of model. And from the segments K to N, the probability of a sample segment belongs to a shape I, segments K for training sets belongs to a training model, giving the mean shape and the covariance matrix. So the probability density function for addressing the segments training patterns Si K to the segment shape class omega. But to do that, we have to assume that we have to assume two iterative process called the expectation maximization algorithm, which is a two-step feed-forward recursive application, recursive algorithm, giving the Q iteration j plus 1, giving iteration at iteration j. The probability of training pattern belongs to a model giving the xi, the whole shape, for a training pattern, the mean shape and the covariance matrix at iteration A, while times the x times the number of natural log of probability, positive probability for a segment to that shape. So T belongs to the shape, K belongs to an I, shape sample I, K the segments, giving the segments mean shape and the covariance mean shape at j+1 step. So this is a complex iterative process. It's recursive from j to j+1, which is the next step to capture the modes of variation for such a training set. So the expectation maximization consists of two steps. Expectation step. What is the expectation step? It involves updating a posterior segment class probabilities. That can be done by using factorization Bayes rules at iteration j+1. So the probability for training set belongs to a model shape. X sub I shape belongs to training set, giving the mean shape and the covariance matrix shape is the probability of that shape over the overall probability times a deformation or mixing proportion value. The quantity epsilon of J of W is the mixing proportion for a training pattern belongs to a model, which is 1/t times the summation of the t to the training patterns and k to the segments. This is the mixed proportion. This is the E step. The M step is to maximize the mean shape and the covariance matrix shape. This is the M shape, the M maximization steps. In maximization shape, we are maximizing the model segments mean shape, which is the posterior probability times the segment shape to the overall training patterns. Likewise, the covariance matrix is the revised estimate for covariance matrix is the same thing of S segment matter minus the mean shape times the segment matter minus the mean shape transpose to construct the revised version of the covariance matrix. I know some notations here are a bit complex, but that's the algorithm. The way to distribute the patterns is giving you the is by using the Gaussian distribution. And Gaussian distribution is plain simple Gaussian distribution to distribute the patterns to the overall models of that set is 2 sigma squared, the squared of the determinant of the covariance matrix to the exponential of the whole thing. Do you have like a paper, a pen here, or no? I just wanted to say something else, but anyhow. Experiment, we have used 14 shape classes. And these are the training sets, part of the training sets, some samples of training sets. To give you more insights, this is training set. And this is only a part. For column number 1 on the left is the sample training sets. Column number 2, sample shape. Column number 3 is the landmark representation of the shapes. Column number 4 is the segments and the initial injection of the EM algorithms. The last column is the output of the recursive EM algorithm. So this is what we have used. This is the output of the EM algorithm after injecting all those sets. for the iterative figure below shows that the segment probability functions, density functions, converges higher than the treating the shape as a whole. So in this way, we have achieved 5 iterations in which the model variations are extracted from the EM algorithm within 5 iterations, rather than 8 iterations for the whole shape. So this is an outstanding. And for classification, this is also sample. So we have used 2 sets, one for training and one for testing and classification. This is the name of the shapes, samples, the number of training sets, number of correct, number of false, and this is the regression rate. So above all, we have achieved 98.3% of regression rate. As you can see, some letters, they are very complex. This is it. Thank you for your attention. If you have any questions.
Why is that low percent last slide?
This one?
Yes.
Yes.
Why is it not good shape? Why this low score? Is low score.
Even though it's segmented, it's probably the miscorrection is regarding to the segmentation process.
Segmentation process is not good.
It's not good.
This is HAM2 is wrong recognized by
because of segmentation. I do not put too much effort on segmentation. I would assume somehow, but the process of segmentation is not as accurate as it should be. But still, some shapes, they are, for example, mean. There is still high regression rate. Yeah, still high regression rate. But some complex shapes, they are low regression rate because of the segmentation process.
As I understood, it's not some neural networks, no?
It's an AI rather than neural networks. AI, because we are using computer vision generated. It's not really a pure. You can consider the EM algorithm as a optimization algorithm. It's mainly used in neural networks, but I have not used in neural networks yet.
Because over 98% of accuracy, it should be overfitting.
98%?
Yes, when it's over 95% accuracy, it is considered as overfitting.
Overfitted?
Yeah, in neural networks, so that's why.
Yeah, but I have not used neural networks. But I don't know whether that's regards to overfitting. Neural networks.
If it is in training data.
But this is classification set.
Okay, on training data sets, you didn't get these results?
No, training sets, I only use training sets to capture the modes. That's it. I have not calculated what is correct, what is bad. Training sets, there is nothing called correct, there is bad. There is only one procedure there, the algorithm, is to extract the modes of variation. That's it. I don't care about whether that pattern is correct pattern or wrong pattern. I don't care about that in the training sets. I care about that for the regression rate, but not as training set. But still overfitting, it's By the way, some scholars, I think that 98 is a bit low also.
But 97, 98, it's over.
It's a matter of opinion, but anyhow,
Like learning.
you see, this should be 100%.
Then it's not neural networks.
It's perhaps not your networks, but should be 100%. But we can never achieve 100% because we are dealing with handwritings and not a machine printed characters.
Okay, we will.